And those are all the answers to the competency questions you have. Just kidding. Ha ha ha. This is behavioral statistics. It's July 30th? It's our last face-to-face class, and no, we haven't gone over the competency, nor would we have all the answers for you here. We're going to start tonight and look at the outline for the correlation and regression unit we're going to cover here. So let's start the ball rolling then as far as what we're going to be talking about here. I came up with a sleep apnea example. Are you guys familiar with sleep apnea? What do you know? What do you know about sleep apnea? What is it?
Stop breathing when you're sleeping.
You basically stop breathing when you're sleeping, and many times when people have it, what is the treatment for it?
CPAP machine.
Yeah, it's a CPAP machine that pushes the air in. It can be peripheral, it could be central, and it's well known that in fact people who have this disorder, many times if you can't get the air in, what ends up happening to these people? You snore. Snoring is a sign that somebody may in fact have sleep apnea. Your assignment for this class, it'll just be class notes, like your usual good outline. You won't really be given any homework problems from this. The homework, which is correlation and regression, will just be part of your competency. But we are going to cover some stuff in the article as well, so to not give you any points for writing all that stuff out seemed inappropriate. So it'll be the same kind of thing here. Any sort of problem you do will be with the competency. So I take 5 people and measure their BMI. BMI is an indicator of what? Body mass index. Do you know anything about the relationship of weight and sleep apnea? Yeah, we know that these things are positively correlated. We know that BMI, the heavier people are, the more they tend to snore, and snoring is an indicator of sleep apnea. So if you look at this example, snoring episodes is our indicator of sleep apnea. There might be a term you might use to describe snoring episodes. Is anybody, I don't think we've said it in this class, operational definition? Have we used that term here before? To operationally define, operational definitions are a mathematical way of defining a variable, a math way of defining a variable. So we're going to operationally define apnea by snoring episodes. You would just pretend for this study that somebody's in a sleep lab. Have you seen these studies before where they can monitor this and you can record this? So we're operationally defining sleep apnea via snoring episodes. BMI is just measured. We have a total of 5 people here, obviously. So the question, the most important question to begin with, is what kind of statistic would you end up doing on this data set? What's the obvious answer? It's a correlation, because we're in the unit with correlation, but is there a better answer than that's what we're doing here? Yes, indeed, this would be what we call a Pearson product correlation. It's in your book, Pearson product. A Pearson correlation. Does anybody know why it's a correlation? Why not a t-test? Why not a t-test here? So you're measuring 2 things here. So that's part of it, but there's another reason why it can't be a t-test here. This is going to be really important for your competency, because on the competency test, you're going to be asked what would be the appropriate statistic to do on this, and why would the others not be appropriate. You won't be asked to do the statistic on that part of the test.
Why is it not cause and effect?
So one reason, you're not manipulating variables. So you're not manipulating variables here, but you could argue if you're looking at gender and snoring episodes that you're not manipulating things either. But you are not manipulating things here. Anything else?
There's not other categories?
Very importantly here, exactly the case that these 2 variables are not, neither one is categorical. Neither one of these 2 variables is categorical. These 2 variables, if they're not categorical, they're classified as continuous. These are continuous variables. Does that make sense? Continuous can range. There's all sorts of possible numbers. If you have two continuous variables, you must do a correlation. Two continuous variables. Think back to the t-test. What did we have? What would be an example t-test? Maybe gender, right? I could look at gender in snoring episodes. Because gender is what?
Kind of.
Well, it's not really manipulated.
You can have male or female.
You could have two levels. It is categorical. For all of the last few weeks, everything was categorical. Levels of a drug. Low, medium, high. Ethnicity. You could have two levels for that. It's not manipulated so much. So if you have two continuous variables, you have to do a correlation. If you have one variable that's categorical with two levels, and the other one is continuous, so one variable is categorical with two levels, and the other one is continuous, what would you do? Just said it. So that was the gender example, right? Male, female, and pain levels. What would you do if the study was, I'm looking at male, female, and snoring episodes? So you have 3 males, 3 females, and you measure the number of... That would be a t-test, independent sample t-test. So what's really, really important, and we're kind of moving actually into the competency stuff because you got to understand this. What if I'm measuring people before and after an intervention? What is that going to be? Well, if it's before and after an intervention, so I take 5 people, measure them on quality of life, and then that was the paired t-test. We're doing a review right now. Just because, why not? So if it's a before and after, that's a paired t-test. What if I look at males and females and I record? That wouldn't be a good example here. I was trying to move to the chi-square situation. Remember we started the semester with that? How many males, how many females? If you just measured frequency, then that would be a chi-square situation. But this one, if you have 2 continuous variables, you must do a correlation. So, a little bit of a divergence there.
That was actually awesome because those kill me. Every time you ask that, I just go blank. Like, I have
Okay.
no idea. I have no idea what to do.
Well, the look on your face was kind of matching that.
Yeah, I'm sure.
So, what's important at the end of this class, and will be part of the competency test, is do you know what statistic is appropriate for what situation? If you're given a situation where you're measuring 2 continuous variables, it's got to be a correlation. If you've got one categorical variable with 2 levels and a continuous DV, that's a T. If you've got a before and after situation, same people twice, paired T. If you've got one categorical variable and it has 3 or more levels, what would that have to be in a continuous DV? So one categorical variable, level of drug, 4 levels, and pain rating. It's got 4 levels, it's got to be what? It's got to be a 1 factor ANOVA. And then if you have 2 categorical variables, gender and drug dose, and you're measuring memory, well, 2 categorical, 2 factor. Questions? Does it kind of make sense?
It will make more after I repeat it several times and write it down.
And if you look at the examples that we covered in each one of those parts, it will make sense. We just haven't used these terms because it's actually when you get to the 2 continuous ones where the contrast becomes, I don't know, more realistic here. So we've got that. If you want to look, getting back to our main story here, if you want to look, we can make what we usually do if we're looking at correlations, 2 continuous variables, we make a scatter plot. SPSS can do this, Excel can do this. I don't know how to get Word to do it, but it's not important that you be able to do this, but that's the representation that we use. Correlations can range. You know how correlations can range? What kind of values we can get for correlations? Can we get a correlation of +2, +3? You guys know what values correlations can range from?
It could be negative or positive.
It could be from -1 to 0 to +1. So correlations can range anywhere from +1 to 0 to -1. What would be the deal as you look at this data? As you look at BMI and snoring episodes, do you think this would be a positive correlation or a negative correlation?
She already answered that. It's positive.
It's a positive correlation. So it looks like as people are heavier, which I just arranged the data that way, what's the case? They snore more. So a positive correlation is indicated when the values of one variable go up, so do the values of the other. So as the values of BMI go up, so do the values of snoring episodes. So as one variable increases, so does the other variable. That's a positive correlation. What if I looked at the relationship between temperature and number of winter coats purchased? Temperature and winter coats purchased.
As the temperature goes down, the purchases go up.
So as temperatures go down, purchases go up. So that would be positive or negative?
Negative.
Negative, also called inverse. That would be a negative correlation. You could say it the other way as well, right? As temperature goes up, winter coats go down. Would that be a correlation situation? Yeah, because they're both continuous, non-manipulated variables. Lots of people like to use correlations because they don't like to take the time to bother to manipulate variables. Just, give them a survey, measure all these things.
So it doesn't prove anything.
So, what's that?
It doesn't prove anything.
Yeah, cause effect is kind of difficult. So you could have a positive correlation, a negative one. Look in your book for a few other examples. I think your book uses SATs and GPAs, which would be probably what kind of correlation? Positive, which is usually good. So we could have positive, negative. Which would be better to get in terms of a correlation? A negative 0.9 or a positive 0.9? Would either one of those be stronger than the other? They're both equally as strong. The number closer to 1 indicates the strength. The sign just says, as this one increases, that one decreases. So the actual number is what measures the strength. What if you get a correlation of 0.01? What if I measured BMI and, I don't know, BMI, well, BMI is related to a lot of things that come to mind. I was going to say asthma severity. What would BMI not be related to? Snoring, how about snoring? Snoring, what's snoring not related to?
Color of your eyes.
Yeah, but color of your eyes is a categorical variable. So that's not much fun. Snoring episodes and income. Right? So let's say you measure a correlation between how much you make and snoring episodes. Let's say you find a correlation of 0.01. R, which is the Pearson correlation, R equals 0.01. Good news or bad news? R of 0.01.
Not really a very strong correlation.
Say again?
It's not really a very strong correlation.
No, don't confuse correlations with p-values. Correlation of 0.01 is near 0. The closer your correlation is to 0, the worse you are. You want correlations away from 0. So, we have two continuous variables here. We have correlations here. Yeah, we can do with this. Here is a printout going down to C here. Get the long number recording. Oh, 14 minutes. It takes forever to convert these things. It's a real pain in the patella. Okay, so I did this with SPSS, and then I just copied and pasted into your screen here. It's a Pearson correlation. What is the important value, or what? Well, let's just go through this. What is the 0.915? Good news or bad news?
Good.
It's good news. It means that's the correlation. So in our data set, there is a strong correlation. What is the probability of getting a correlation of 0.915 due to chance? How often do you get this correlation due to chance? This result will occur about 3% of the time due to chance, 0.029. So a correlation of 0.915 is very strong. It's close to what? It's close to +1. Sign matters here. It's close to +1. So that says, yes, indeed, there is a good relationship, a strong relationship. The more you weigh, the more you snore. And the 0.029 says this is what? Statistically significant. Let's see if we can write out the R statement. So I was just in Hawaii and my friend out there would have said R, 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 R. He's like that. Did you see they almost had a tropical system hit Hawaii? And then it was like nothing by the time it got there. Jim Cantori was reporting, oh, we're being smacked by, what was the storm? Flossie? Flossie. And he's standing in Hilo and it's like drizzling. But anyway, so you'd write the letter, which would be what? R, and then in parentheses, do you remember what you have in parentheses? Your degrees of freedom. So what do you think the DFs will be here? Not quite 101, just one number here. You have 5 pairs here, so you would guess 4, but for correlation it's n-2, because a circle or correlations are based on a best fitting line, and you need 2 points. You don't really need to write that down. n-2. Let me get out of here. So you would write R and then in parentheses 3 equals what? Positive 0.915 plus 0.915 and then comma P you could technically write P less than 0.05, but the more appropriate way is if you've got an exact value, you write P equals 0.029. P equals 0.029. This result is statistically significant. What would be your real world statement? Your real world statement. That as
BMI increases, the incidence of snoring.
there you go. As BMI increase, so does snoring and probably sleep apnea. Are we good with that?
Do we make that jump? And so
Yep.
probably sleep apnea?
Yeah, if we are operationally defining sleep apnea by snoring frequency, we can make that statement. Uh-huh.
Can you give the not real world statement before that again?
So this result is statistically significant? Or the R?
Yes.
R and then in parentheses 3 equals 0.915, comma P equals 0.029. I better cut off the tape at this point.